At first glance, most pneumatic control equipment seems like a maze of bellows, cams, beams, and other mechanisms packed into a small area. Sometimes the design makes it appear as if the instrument is hard to understand. However, many of these instruments are fairly easy to understand if you know what you're looking for. Some pneumatic instruments, like this manual control station, are purely mechanical devices. They often use a series of manual valves to control an air pressure signal. But the majority of pneumatic instruments control or transmit air pressure signals automatically by balancing themselves in response to changes in input pressure. All self-balancing instruments have three basic mechanisms: input, error detector, and output balancing. The input mechanism for this valve positioner is a bellows. It converts a change in a process variable into mechanical motion. The mechanical motion is sensed by an error detector mechanism, which converts the motion into a proportional back pressure. A pilot valve assembly is a common type of error detector mechanism. This spring is the output balancing mechanism for the positioner. The spring is used to restore balance to the instrument. The new balanced position reflects the change in input pressure and results in a proportional change in output pressure. Identifying these basic mechanisms is an important part of understanding how self-balancing instruments operate. Another important part is understanding how these mechanisms work together to balance the instrument. There are two general ways in which self-balancing instruments operate. One way is to balance an input force with a balancing force. You'll often hear these instruments referred to as force balance instruments. Some instruments achieve balance by balancing an input motion with a balancing motion. These instruments are generally called motion balance instruments. In this program, we'll look at a few types of force balance and motion balance instruments in greater detail. We'll see how they operate and where common adjustments are located. Knowing how a particular instrument balances itself, as well as being able to find the input, error detector, and output balancing mechanisms, makes repairing and calibrating the instrument a lot easier and quicker. Now, before we look at actual force balance and motion balance instruments, let's see what is meant by force and motion balance. Here's a simplified illustration of a force balance instrument. This bellows is the input mechanism for the instrument. The input bellows receives a pressure signal that represents the condition of a process variable. The input bellows exerts a force, the input force, on one end of a beam. The beam is pivoted at its center. A flapper extends up from the center of the beam. The flapper's position relative to a nozzle depends on the movement of the beam. The flapper and nozzle make up the error detector mechanism for the instrument. Supply air enters here and flows through a restriction. The restriction reduces the forcing effect of supply air on the flapper. It also makes it possible to position the flapper relative to the nozzle. The position of the flapper relative to the nozzle determines how much back pressure builds up in this back pressure compartment. We'll use this pressure gauge as an indicator to show the value of back pressure. Back pressure is used for two purposes. First, it's the output pressure. The output pressure is proportional to the input pressure and is a reflection of the process variable that the instrument is monitoring. Back pressure also determines how much pressure is applied to this bellows. We'll call it a balancing bellows, since it serves as the instrument's output balancing mechanism. The balancing bellows in this case provides the balancing force for the instrument. Right now we're looking at the instrument in a balanced state, meaning that the input force equals the balancing force. Now, if input pressure were to change, several things would happen. We'll go through each of them separately. Suppose the process variable changes so that input pressure increases. The input bellows expands, pushing up on one end of the beam. So the input force has changed and the balance has been disrupted. When the beam tipped, it moved the flapper closer to the nozzle. This restricts the flow of air from the nozzle, increasing back pressure in the back pressure compartment, as indicated by the gauge. This increased back pressure causes the balancing bellows to expand. The balancing bellows exerts a force, the balancing force, that tips the beam in the opposite direction. The flapper moves away from the nozzle, assuming a stable position. At this new position, the input force once again equals the balancing force. This position results in a new output pressure, which is proportional to the change in input pressure. So the instrument has automatically responded to the increased input pressure by balancing the input force from the input bellows with the balancing force from the balancing bellows. We've just seen one way in which force-balanced instruments operate. Actual instruments often contain different mechanisms, which can cause the instrument to be balanced in a different position. But even though force-balanced instruments may not balance in the same way, all of them operate by balancing forces. Another way in which self-balancing instruments operate is by balancing motions. In general, motion-balanced instruments use input and balancing motions instead of forces. We'll use this simplified illustration of a motion-balanced instrument to describe how opposing motions are used to balance the instrument. Once again, input pressure enters an input bellows, which acts as the input mechanism. As the bellows expands or contracts, motion is produced in this lever. This is the input motion for the instrument. Now, this is different from the force balance instrument shown earlier, in that input pressure is converted into the motion of a lever. This lever is part of a three-lever system. There are two fixed levers, both of which pivot at the center. What we mean by fixed is that the pivot doesn't move. In motion balance instruments, any fixed levers will usually turn as a result of the rotation of a shaft. But we'll show the levers as pivoting to keep things simple. There's also a floating lever, which is free to pivot at both ends. We'll look at how all three levers react to an input motion in just a second. A flapper extends up from the center of the floating lever. A flapper nozzle arrangement is the error detector mechanism. The movement of the floating lever determines the position of the flapper relative to the nozzle. Supply air enters here, flows through a restriction, through the nozzle, and is forced against the flapper. Here's the back pressure compartment. Once again, we'll use a pressure gauge to indicate the value of back pressure. Back pressure is used as the output pressure, and it's also fed to another bellows, which serves as the output balancing mechanism. We'll refer to this bellows as a balancing bellows. As the balancing bellows expands or contracts, movement is produced in this fixed lever, just like in the other fixed lever. This is the balancing motion for the instrument. Let's see how the instrument responds to an increase in input pressure. Again, a number of things happen. The input bellows expands, pushing one end of the fixed lever down. This is the input motion. As a result, this end of the fixed lever moved upward. Since the floating lever is attached to the fixed lever, it also moved, bringing the flapper closer to the nozzle. Now, this results in an increase in back pressure, as indicated by the gauge. With the increase in back pressure, the balancing bellows expands, pushing down on the other fixed lever. This is the balancing motion for the instrument. The flapper is pulled away from the nozzle until it stabilizes at a new position. The instrument has responded to a change in input pressure by balancing itself, but this time the balance is achieved by resolving different motions instead of forces. The increase in input pressure has once again been converted into a proportional increase in output pressure. Now, the illustrations we just looked at are just that, illustrations. Now, as you can see, the actual instruments look a lot different and may seem hard to understand. But no matter how different these instruments may appear, they operate pretty much the same way. Changes in input pressure cause the instrument to be unbalanced. The instrument then balances itself so that the output pressure is once again proportional to input pressure. Most self-balancing instruments can be divided into two groups: force balance instruments and motion balance instruments. If you know how a particular instrument balances itself, even if it's unfamiliar to you, you've got a good head start in understanding how it works, where potential repairs may need to be made, and how to make calibration adjustments on it. In upcoming parts of this program, we'll be looking at actual force balance and motion balance instruments. We'll concentrate next on force balance instruments. For now, look over the text material and make sure you know the basic difference between force balance and motion balance instruments. Force balance instruments, like these, operate by balancing an input force from an input mechanism with a balancing force from an output balancing mechanism. There are two common designs of force balance instruments. One design places the input and balancing forces directly against each other. We'll talk more about this type of instrument in the next segment. The other common design of force balance instrument balances forces on a beam at distances from a fixed pivot. Now, sometimes there may be one or more beams and one or more different pivots, but the net effect is still the same. The instrument responds to changes in input pressure by balancing forces. The idea of balancing forces at distances from a fixed pivot is used by many different instrument manufacturers for a variety of purposes. But whether the instruments are used as valve positioners or as transmitters, they all work basically the same way. You may hear these force balance instruments called moment balance instruments. And this is true because a moment is defined as a force exerted at a distance from a pivot. For the remainder of this segment, we'll talk about how this design of force balance instrument operates. We'll use this differential pressure, or DP transmitter, as an example. Now, this transmitter senses changes in the difference between two related pressures and converts that difference into a pneumatic signal, which is then sent to a remote plant location. Now, as you can see, this instrument is oriented in a vertical direction, unlike the illustrations we saw earlier. Even so, it still balances an input force with a balancing force to produce an output pressure. We'll use a simplified cutaway of the transmitter to identify its basic mechanisms. Its input mechanism is a bellows capsule. A bellows capsule consists of a metal bellows which is sealed inside a protective can or capsule. The bellows capsule is subjected to two different input pressures, the higher of the two pressures through this port and the lower pressure through this port. Any change in differential pressure causes the bellows capsule to move. The capsule provides the input force for the instrument. The input force is exerted on a beam called the force beam. The force beam pivots on a flexible seal, which allows small movements of the beam. The flexible seal is also used to isolate the lower part of the DP transmitter, so that the pressures are sealed within the transmitter. A flapper and nozzle arrangement at the top of the instrument is the error detector mechanism. The flapper is attached to a second beam known as the range beam, which is connected to the force beam by this linkage. So when the force beam moves, the range beam also moves. The range beam pivots on a special type of fulcrum, a floating fulcrum. It's called floating because it can be adjusted to change the range of the transmitter. We'll look at this in more detail later on. The output balancing mechanism is a bellows, located near the bottom of the range beam. This bellows is used to provide the balancing force for the instrument. Now, to see how this instrument responds to an increase in differential pressure, let's look at a more basic illustration. Here are the two input ports, the high pressure port and the low pressure port. The bellows capsule, represented by this symbol, moves in response to the difference in the two pressures. Here we have the force beam, which pivots on the flexible seal. We've simplified things by using a pivot to represent the seal. The force beam is connected to the range beam, which pivots on the floating fulcrum. The movement of the two beams positions the flapper. Supply air enters here, flows through a restriction, through the nozzle, and is forced against the flapper. The back pressure chamber is here. It's connected to this block labeled R, which represents a pneumatic relay. The relay also has a connection to supply air that enables it to operate. For the purpose of this example, the relay's function is to increase the volume of air so that changes in back pressure can be converted into proportional changes in output pressure. The output pressure can then be transmitted to a remote location. We'll use a pressure gauge to indicate the value of the output pressure as back pressure changes. The relay also provides enough pressure to cause the balancing bellows to expand and initiate the balancing force for the transmitter. We'll go into how relays operate and why they're necessary in a separate part of this program. Okay, say differential pressure increases. This means the difference between the high and low pressures increases, causing the bellows capsule to move the lower end of the force beam in this direction. This is the input force for the instrument. When the bottom of the force beam moved this way, the top of the beam moved this way, pulling the top of the range beam with it. As a result, the flapper moved closer to the nozzle, increasing back pressure in a back pressure compartment. Back pressure is fed to the relay, which converts it into a proportional output pressure. Output pressure is, in turn, fed to the balancing bellows, which expands. The bellows now pushes on the lower end of the range beam, which pivots about the floating fulcrum. This caused the upper end of the beam to move in the opposite direction. This movement pulled the flapper away from the nozzle. It assumes a position that reflects a new balanced state for the instrument. For this instrument, the balancing force isn't exerted directly by the output balancing mechanism. Instead, the balancing force is obtained by the pull of the range beam on the force beam. So when the instrument is in balance, the input force provided by the bellows capsule input mechanism times its distance from the pivot equals the balancing force, the pull on the force beam by the range beam, times that distance from the pivot. The new output pressure is proportional to the change in differential pressure. Now, this DP transmitter is just one of many force balance instruments that operate by balancing forces on a beam at distances from a fixed pivot. Your text contains information about other instruments that use variations of this design. Now, it's your job to see that pneumatic control equipment is properly calibrated. The procedures that you'll follow when you calibrate a particular instrument depend on the process and the design of the instrument. Typically, self-balancing instruments have two calibration adjustments, a zero adjustment and a span or range adjustment. Instruments may have other adjustments, such as a linearity adjustment, but we'll limit ourselves to the two most common adjustments. A zero adjustment is a device that enables you to set the low end of an instrument's pressure range. By adjusting it, you set the instrument's output pressure to be at its designed minimum when its input is at its designed minimum. For this DP transmitter, the zero adjustment is a screw adjustment located here underneath the balancing bellows. The adjustment that's made to set the high end of an instrument's pressure range is called a span or range adjustment. Span is the difference between the highest and lowest pressure that an instrument can measure. Range is the upper and lower pressure limits of that measurement. Manufacturers sometimes use the terms span adjustment and range adjustment interchangeably. Here's how you can tell them apart. When an instrument has a fixed range, it will usually have a span adjustment. When an instrument has a range that can be extended, you're likely to see a range adjustment instead of a span adjustment. Now, in either case, the adjustment is made to set the high end of the instrument's pressure range so that the instrument provides its maximum designed output pressure when its input pressure is maximum. Now, this DP transmitter has a range adjustment, a wheel. We identified it earlier as a floating fulcrum. Floating because it's mounted on a lock nut and it can be moved up or down the threads on the range beam. Both the zero and the span or range adjustments affect the balance of a self-balancing instrument. How these adjustments affect the balance of this DP transmitter is discussed in your text. Now, as a general rule, always look over the instrument's data plate, the manufacturer's instruction manual, and your plant's calibration file before you calibrate any pneumatic control equipment. These sources of information provide valuable knowledge about where specific adjustments are located, what pressure ranges the instrument is designed to handle, and what specific calibration procedures should be followed. The DP transmitter we discussed in this segment is typical of moment balance instruments, which are force balance instruments that operate by balancing forces on a beam at distances from a fixed pivot. However, some force balance instruments don't use beams or pivots at all. They balance themselves another way, by placing the forces in direct opposition to each other. We'll look at an example of this design when we return. At this time, read over the text material and have your instructor clear up any questions you have before we move on. Now, both of these instruments are force balance instruments. However, they don't operate like the force balance instruments we saw earlier. For these instruments, the basic mechanisms are lined up along a horizontal or a vertical axis. Now, this design places the input and balancing forces directly against one another, rather than balancing them at distances from a fixed pivot. In fact, if we could see inside this instrument, it would almost look like the input, error detector, and output balancing mechanisms were stacked on top of each other. Because of that appearance now, this design is often referred to as a stack type, or true force balance design, since the forces are placed in direct opposition without using beams or pivots. Now, in this DP transmitter, the basic mechanisms are stacked along a horizontal axis. Let's look at a cutaway illustration to identify them. The input mechanism for this stack-type force balance instrument is a diaphragm. It's known as a sensing diaphragm because it senses changes in differential pressure. The sensing diaphragm flexes in response to changes in differential pressure. There are 4 input ports for the transmitter to allow for differences in connecting pressure tubing to the instrument. Only 2 of the ports are used for normal operation. For the purposes of this illustration, we've plugged this set of ports. The high pressure port is here, and the low pressure port is here. Supply air enters here, flows through a restriction, and through the output port. The sensing diaphragm is attached to a shaft called a thrust shaft. On one side, the shaft is connected to a spring, which is in turn attached to the instrument housing. On the other side of the diaphragm, the thrust shaft is connected to another diaphragm, a balancing diaphragm. The balancing diaphragm acts as the output balancing mechanism for the instrument. The shaft is sealed by these bellows so that it moves without any interference from the input pressures. These vents keep the bellows from expanding and enable the shaft to move in response to differential pressure only. One side of the balancing diaphragm forms half of the error detector mechanism. As this diaphragm flexes, it moves closer to or farther away from a nozzle. The nozzle is vented at one end, unlike the nozzle arrangements that we've seen so far. However, its function as an error detector mechanism isn't any different. The position of the balancing diaphragm relative to the nozzle determines how much back pressure builds up in a chamber that surrounds the nozzle. As you can see, all of the basic mechanisms are aligned with a center line in the instrument. Both the input and balancing forces are exerted directly against each other in a linear direction. To see how the transmitter responds to an increase in differential pressure, let's use a more basic illustration. In this illustration, there's a high pressure port and a low pressure port. Here's the sensing diaphragm, which is the instrument's input mechanism, the thrust shaft, and the balancing diaphragm, which is the instrument's output balancing mechanism. The diaphragm's position relative to the nozzle determines the amount of back pressure in this compartment by varying the amount of air bleeding out this end of the nozzle. Now, the actual distance from the balancing diaphragm to the nozzle is very small, a fraction of an inch. We've exaggerated the distance in order to show how the instrument responds to changes in differential pressure. Supply air enters here, flows through the restriction, and enters the back pressure chamber. Output pressure leaves the transmitter through this port. Again, we'll use a pressure gauge to show the value of output pressure as back pressure changes. We'll assume that the instrument is initially in balance. Now suppose the differential pressure increases. The sensing diaphragm flexes in proportion to the increase in differential pressure. This is the input force for the instrument. When the sensing diaphragm flexes, the thrust shaft moves the balancing diaphragm closer to the nozzle, restricting the flow of air through it and resulting in an increase in back pressure. The increase in back pressure acts on the balancing diaphragm, causing it to flex in the opposite direction. This is the balancing force for the instrument, exerted in a straight line and opposite to the direction of the input force. The balancing diaphragm assumes a position that reflects a new balanced state for the instrument. This corresponds to the change in differential pressure. The new position actually reflects a balance between the input force provided by the sensing diaphragm and the balancing force provided by the balancing diaphragm. Output pressure is once again proportional to differential pressure. For most stack-type force balance instruments, the input and balancing forces directly oppose each other. No levers or pivots are used to balance the forces, as was the case with the force balance instruments we examined in the last segment. Now, the calibration adjustments for this DP transmitter are located at opposite ends of the instrument. The zero adjustment is here, nearest the sensing diaphragm. For this instrument, the zero adjustment is a simple screw adjustment. The manufacturer refers to this transmitter as a fixed range DP transmitter, meaning that its range is not adjustable. So it has a span adjustment here, nearest the balancing diaphragm. For this instrument, the span adjustment is a hex nut that's turned to move the nozzle further into or out of the transmitter housing. Both the zero and span adjustments for the transmitter are located along the instrument's center axis, just like the instrument's basic mechanisms. Turning these adjustments ensures that the transmitter is properly calibrated so that it responds correctly to its designed pressure range. As we mentioned earlier, calibration procedures are different for each application. Always look over the instrument's data plate, its instruction manual, and your plant's calibration file before you attempt any calibration procedure on a self-balancing instrument. For the past few minutes, we've seen two different designs of self-balancing instruments that operate by balancing forces. In one design, the forces are balanced on a beam at distances from a fixed pivot. In the other, the forces are balanced by placing them in direct opposition to each other, by literally stacking the basic mechanisms along a center line in the instrument. But in either case, the instrument achieves balance by balancing forces in one way or another. Any changes in the instrument's input pressure result in proportional changes in its output pressure. Now that's just one way in which self-balancing instruments can operate. In just a moment, we'll look at self-balancing instruments that operate by balancing motions instead of forces. Take the time now to read over the text material on stack-type force balance instruments. Be sure that you understand how these instruments operate before we go on. Up to now, we've been looking at self-balancing instruments that balance forces in order to convert an input pressure into a proportional output pressure. But other self-balancing instruments work differently. They're called motion balance instruments because they operate by balancing input and balancing motions instead of forces. Now, these are common types of motion balance instruments. For the most part, motion balance instruments can perform the same general functions as force balance instruments. They're commonly used as valve positioners, transmitters, and controllers. Now, the key to understanding how motion balance instruments operate and how they're calibrated is no different from understanding force balance instruments. First, find the basic mechanisms in the instrument. Once you do that, you can determine where the input and balancing motions occur and how the instrument balances itself. We can divide motion balance instruments into two groups based on their design. One design, which is used in this pressure transmitter, balances motions in a linear direction. We'll talk more about this design in the next part of this program. Now, over here, we have another type. This valve positioner employs the other common design of motion balance instruments. It places the input and balancing motions at an angle to each other. Now, this positioner regulates the amount of air pressure flowing to an actuator that is connected to a valve stem. The output pressure from the positioner causes the actuator stem to position the valve. The positioner's ability to cause the actuator to position the valve accurately depends on it being able to convert an input pressure into an input motion and balancing that motion with another motion. For this instrument, the balancing motion is at an angle to the input motion. Let's look at the positioner's basic mechanisms. Input pressure is applied to the instrument's input mechanism, a bellows. The bellows exerts a force on one side of a flexure spring and link and ball assembly. The spring, link and ball assembly, convert input pressure to the instrument's input motion. A flapper nozzle arrangement is the error detector mechanism. The balancing motion is provided by the turning or twisting action of this shaft. The shaft is normally connected at this end to the valve stem through a linkage. The other end of the shaft is connected to the other side of the flexure spring. The input motion provided by the bellows and the flexure spring slides the ball in this direction. The balancing motion provided by the twisting action of the shaft on the spring moves the ball in this direction. As you can see, the balancing motion is at an angle to the input motion. We'll use a simplified illustration to see how this instrument responds to an increase in input pressure. In the illustration, this is the positioner, which is attached to an actuator and valve stem. The actuator and valve are used in this example to control fluid flow in a pipe. We've exaggerated the size of the positioner so that we can see how it responds to an increase in input pressure. This bellows is the positioner's input mechanism. Here's the flexure spring and link and ball assembly. The ball slides along the flapper and positions it relative to the nozzle. This determines the amount of back pressure in the back pressure compartment. Both the flapper and the nozzle are located on a platform, which is really a rotating disc. The disc can be turned to adjust the positioner depending on whether you want the valve to open or close as input pressure increases. The specific calibration adjustments for this positioner are explained in greater detail in your text. Supply air enters here, flows through a restriction, through the nozzle, and is forced against the flapper. Supply air is also fed to a relay, which is connected to the back pressure compartment. The relay's function, once again, is to increase the volume of air so that output pressure from the positioner can be sent to the actuator to cause the valve stem to move. This pressure gauge will indicate the value of the output pressure as back pressure changes. When input pressure increases, the bellows expands, pushing against one side of the flexure spring. As the flexure spring compresses, the ball tip slides on the flapper so that the end of the flapper moves closer to the nozzle. This is the input motion for the instrument. With the flapper closer to the nozzle, back pressure and output pressure, as indicated by the gauge, increase. The increased output pressure caused by the input motion reflects the increase in input pressure. Now that we've seen how the input motion is developed, let's examine how the balancing motion is developed. The output pressure from the positioner is fed to the actuator, which will cause the valve stem in this example to move upward. The movement of the valve stem originates the balancing motion for the instrument. As the valve stem moves up, it twists the shaft and the flexure spring. This twisting action caused the ball tip to move, positioning the flapper away from the nozzle. This is the balancing motion for the instrument, at an angle to the input motion. The ball tip assumes a position that reflects the new balanced state for the instrument, one in which there's a balance between the input and balancing motions. The position of the ball tip ensures that any change in input pressure is converted to the proper amount of actuator motion. In this manner, a valve can be positioned exactly where it should be for a given input pressure. Now, this valve positioner is just one of many types of motion balance instruments. For this instrument, the input and balancing motions are placed at an angle to each other. Now, there's another common design of motion balance instruments that balances two linear motions. We'll look at this design when we return. But before we do that, review the material in your text on what we've covered in this part of the program. In the last segment, we looked at this valve positioner, a motion balance instrument that balanced motions placed at an angle to each other. Well, here's another design of self-balancing instrument that operates by balancing motions, but for this motion balance instrument, a pressure transmitter, the motions aren't placed at an angle to each other. Instead, the input and balancing motions are linear. Now, this design is often called a linear motion balance design because the instrument balances itself by balancing two linear motions. The input pressure is applied to a helical bourdon tube element. This is the input mechanism for the instrument. The bourdon tube tends to curl or uncurl in response to changes in input pressure. The tip of the bourdon tube is connected by this linkage to a rod, which moves up or down in a linear direction as the bourdon tube curls or uncurls. This is the input motion. Now, in order to see the transmitter's other basic mechanisms, let's look at a cutaway view. The error detector mechanism is a variation of a pilot valve. A plunger at the top of the rod serves as a plug. The movement of the rod determines how much of the plunger is drawn into this opening, which serves as the variable restriction. The output balancing mechanism for the instrument is a dual bellows assembly. The two bellows are securely fastened together by a center post, so if one of the bellows moves, the other one moves as well. The bellows assembly is free to move in a vertical direction, limited by this spring underneath one of the bellows. We'll see in a moment how the movement of the bellows assembly is the balancing motion for the instrument. Now, supply air enters the instrument through this port, flows through a fixed restriction, and bleeds out the variable restriction. Even though the variable restriction and the plunger appear to be a pilot valve error detector mechanism, they function much more like a flapper and nozzle arrangement. The position of the plunger relative to the restriction determines the amount of back pressure that's present in each of the bellows in the dual bellows assembly and in this chamber. This diaphragm and pilot valve assembly above the chamber functions as a relay. The relays fed back pressure through this port and supply air through this port. The relay's function, once again, is to convert changes in back pressure into proportional changes in output pressure. In order to show how the instrument responds to an increase in input pressure, let's go to a more basic illustration. Here's the rod that is connected to the bourdon tube, the instrument's input mechanism. A plunger is attached to the top of the rod. Its position relative to the opening here determines the amount of instrument back pressure. Together, the plunger and the variable restriction comprise the error detector mechanism. The output balancing mechanism is the dual bellows assembly, whose movement is limited by the spring. Supply air enters the instrument here, and the fixed restriction is here. This block represents the relay. A pressure gauge will indicate the value of output pressure as back pressure changes. Output pressure leaves the transmitter here and is fed to this chamber above the bellows assembly. Let's see what happens when input pressure to the transmitter increases. An increased input pressure causes the rod to move downward. This is the input motion, initiated by input pressure acting on the bourdon tube, and the motion is linear, in this case, in a downward direction. The plunger is drawn towards the variable restriction, reducing the amount of air that bleeds out of the restriction and increasing back pressure in the dual bellows assembly. The increased back pressure is fed to the relay. It converts the change in back pressure to an increased output pressure, which is fed to the chamber above the bellows assembly. The increased output pressure forces the assembly downward, actually moving the variable restriction away from the plunger until it assumes a position that reflects a new balanced state for the instrument. When this happens, output pressure is once again proportional to input pressure. The downward movement of the bellows assembly is the balancing motion for the instrument. This motion is also linear, and as you probably have noticed, is in the same direction as the input motion. Now, this pressure transmitter is a typical example of a linear motion balance instrument. The instrument balances itself by balancing linear input and balancing motions. Both the zero and span adjustments are at the bottom of this instrument. The zero adjustment is this collar located on the rod. The range on this transmitter isn't adjustable, so it has a span adjustment on the connecting linkage between the rod and the bourdon tube. The instruments we've been looking at for the past few minutes are just two typical examples of motion balance instruments. You may be asked to repair or calibrate other types of self-balancing instruments that operate by balancing motions. In general, there are two basic designs of motion balance instruments. In one common design, the instrument balances input and balancing motions that are applied at an angle to each other. In the other, the input and balancing motions are linear. I'll take a few minutes now to read the text material dealing with linear motion balance instruments. When we return, we'll look at pneumatic relays. Pneumatic control systems often contain many interrelated instruments. Now, these instruments work together to take a pneumatic signal that represents the value of a process variable and use it for indicating, recording, protection, or controlling purposes. The signal sometimes undergoes changes at various points in the system, depending on the needs of the system. Pneumatic relays are used in many control systems. Essentially, a pneumatic relay is a device that uses one pneumatic pressure or signal to control another signal. Some types of self-balancing instruments cannot operate without a relay. Now, these relays, often called signal boosting relays, are small devices built in as part of the instrument. The purpose of a signal boosting relay is to increase the volume of air so that small changes in back pressure are converted into proportional changes in output pressure that can be transmitted over long distances. But relays can also be separate instruments, separate components of a pneumatic control system. For the most part, these relays have a slightly different purpose. They modify an input signal, change it in some way to produce an output signal necessary to meet the demands of a particular control system. Now, the term relay can be confusing because various manufacturers and diagrams identify different types of instruments as relays. For instance, some controllers can be used as relays. You're likely to find many different types of pneumatic relays in your facility. Knowing basically how relays operate will help when you repair or install them. We'll limit our discussion of relays by talking about two basic types. The first type, which is used on this DP transmitter that we saw earlier, is called a signal boosting relay. Generally, this type of relay uses back pressure to control the output signal of a self-balancing instrument. Here's a simplified drawing of this type of relay. Back pressure from an error detector mechanism enters the relay here and builds in a compartment. We'll use this pressure gauge to indicate the value of back pressure. A diaphragm separates back pressure from the rest of the relay. The diaphragm flexes in proportion to the amount of back pressure in the compartment. A metal base in the center of the diaphragm connects it to a pilot valve. At the other end of the pilot valve, there's a spring whose tension limits the amount of pilot valve travel. As the pilot valve moves, it varies two restrictions simultaneously. This plug varies this restriction, which controls the amount of supply air that enters the relay. This plug varies this restriction, which controls how much supply air is exhausted from the relay. The amount of supply air that is allowed to flow into the relay depends on the position of the pilot valve, whose movement is controlled by the movement of the diaphragm. In this way, the relay increases the volume of air so that changes in back pressure are converted into proportional changes in output pressure. If back pressure increases, the diaphragm flexes downward. moving the pilot valve downward and compressing the spring. The pilot valve assumes a new position that reflects the change in back pressure. This allows more supply air to flow into the relay and less air to be exhausted from it. So in this relay, we've taken a small change in back pressure and converted it into a proportional change in output pressure. The small volume of back pressure entering here has been converted into a proportionally larger volume of air that leaves the relay as output pressure. The relay that we've just examined is a simplified example. Actual relays differ from manufacturer to manufacturer. The relay can have several different elements inside its housing, but its basic purpose is the same. It converts back pressure into a usable output pressure. Relays can also be separate components of a pneumatic control system. Relays like these have a slightly different function. They modify an input pressure signal in some way so that the output pressure signal from the relay can be used for a particular purpose in a control system. Now, although you might not think of a regulator as being a relay, it's actually a manually operated relay. A regulator takes supply air, usually at a fixed value such as 40 psi, and provides a lower output signal, also at a fixed value such as 20 psi. Regulators use manual means to produce a lower output pressure. For this regulator, the control is a knob on top of the regulator. Turning it puts tension on a spring inside the regulator, which exerts a force on an inner diaphragm assembly. You turn the knob until you get the desired output pressure, as shown by a pressure gauge either on the regulator or in the output pressure line. At that point, the regulator has controlled supply air, so that the output signal is at a steady, lower value. Relays can also modify an input signal automatically, and they're capable of performing specific functions in a pneumatic control system. Some relays can perform simple arithmetic functions, such as providing an output signal that is equal to the sum of two or more input signals. Other relays can perform even more complex functions, such as selecting the lowest of two or more input signals to generate an output signal. Most relays that operate automatically are simplified stack-type force balance instruments. They operate by balancing input and balancing forces placed in direct opposition to each other. Any changes in the input signal to the relay are reflected in proportional changes in the relay's output. Now here's a special purpose relay called a reversing relay. Now it's so named because it provides an output that decreases in proportion to increases in the input signal. In this simplified illustration of a reversing relay, the input signal enters the relay and fills a chamber between two diaphragms, an upper and lower diaphragm. The diaphragms are connected so that they work as one assembly. When one diaphragm flexes, the other one flexes as well. A pilot valve is located near the bottom of the relay. This pilot valve looks a little different from the ones we've shown you so far, but it still operates by varying two restrictions simultaneously. This ball plug controls supply air flow into the relay. The other plug controls how much air is exhausted from the relay. Air is exhausted through this tube at the center of the diaphragm assembly. In its present condition, the relay is not exhausting air because the plug is seated in the opening to the tube. A spring is attached to the ball plug. Another spring is attached to the relay housing above the diaphragm assembly. Its tension limits the movement of the assembly. This pressure gauge will indicate the value of input signal entering the relay, and this gauge, the value of the output signal leaving the relay. Now let's see why this relay is called a reversing relay. Suppose that the input signal increases. Both diaphragms flex upward because the upper diaphragm has a greater surface area than the lower diaphragm. This is the input force for the relay. The pilot valve also moves upward, but its travel is limited by the spring and the supply restriction, creating a gap between this plug and the exhaust tube. As a result, air is exhausted from this chamber through the tube to atmosphere. This decreases the output pressure signal. which decreases the input force because there's less pressure on the lower diaphragm. This spring now forces the diaphragm assembly downward, closing off the exhaust tube until the diaphragm assumes a position that reflects a new balanced state for the relay. The opposing force that the spring exerts on the diaphragm assembly is the balancing force for the relay. The input force from the diaphragm assembly once again balances the balancing force supplied by the spring. But this time, the output pressure signal is inversely proportional to the input pressure signal. An increase in the input signal has resulted in a decrease in the output signal. Of course, the reversing relay works the other way too. Its output increases if input decreases. The important thing to remember is that the relay has balanced forces to automatically convert an input pressure signal into a usable output pressure signal. Now, this reversing relay is typical of pneumatic control equipment that operates by balancing itself in response to changes in input pressure. You may be responsible for repairing and calibrating many different types of self-balancing instruments. When you first look at some of these instruments, they may seem pretty difficult to understand, but their principles of operation are fairly easy. Most self-balancing instruments can be divided into two groups: force balance instruments and motion balance instruments. If you know how an instrument balances itself and where the instrument's basic mechanisms are located, you can figure out how the instrument works, even if you've never seen it before. For now, read over the text material that deals with pneumatic relays. Then go back over any of the other sections if you need to. Be sure that you understand force balance instruments, motion balance instruments, and pneumatic relays.